All right, everyone. Well, this is going to be our first video of the semester, and we're going to be talking about section 4.5 in here, triple integrals, taking integration to the next level. I'm going to be making a bunch of different videos to hopefully try to cover all the different content that we're supposed to have for this week, and then start working ahead to some stuff that we'll cover after spring break as well. Okay. But you'll kind of see how that stuff plays out as we move along. So let's just go ahead and jump in here to 4.5 triple integrals. We'll see kind of how all this works. Okay, here's at least the basic idea. Suppose we want to take the integral of a function that has 3 variables in it, but over a rectangular box. And maybe the box is given by the following. So like if I look at this picture down here, any box is going to have some sort of a bound on its x coordinate, some bound on its y, and some bound on its z coordinate. So there are a lot of different reasons why I might be interested in kind of like integrating some variable of 3 functions, but at the moment we don't really have good grounding for why we would care about some of that, but we'll get into that in some of the later sections. Ultimately though, our strategy for doing this, as I state here, is going to be analogous to what we did with double integrals. We can imagine kind of chopping up this rectangular box into a bunch of little smaller rectangular cubes, and if I can kind of find the volume of each one of those, I can kind of add all of those up to get an approximated volume for the entire figure. Now there's a couple of technical things that go on here in terms of doing this when I have non-box-like regions, but we're going to skip some of those details and just kind of go down right to what the definition would ultimately look like. So our definition here for a triple integral of a function over a box is given as follows. So I do a triple integral over a box. That's the function that I'm integrating. And then I don't have little bits of area now that I'm chopping up, but I kind of have these little bits of volume that I'm working with. So this is kind of a new interesting switch. This would be the same thing as saying that, again, if I kind of added up all of these little boxes and kind of did this triple sum over all of them, and then applied a limit as the number of boxes or the number of cuts in each dimension kind of went off to infinity. Okay. So this, of course, provides that the limit exists, and we have our sample point selected within each box. This is a very complex definition, but ultimately, there's a really great way that we can begin to handle it. If f is a continuous function on that rectangular box, again, expressed here as bounds for x, bounds for y, and bounds for z, then we have kind of an updated idea of Fubini's theorem. We had a Fubini's theorem for double integrals, and we have another one now for triple integrals. And here's what it says, that if I was going to be doing a triple integral of our function, f, x, y, z, over our box, that is identical to integrating from a to b, and then from c to d, and then from r to s with our particular function. So this is actually going to look like exactly kind of how we set up a double integral with an iterated integral. We kind of have this new 3 or triple integral version of an iterated integral sitting here. Okay. Oh, you might be able to tell that as I wrote this down, I definitely wrote some stuff in the wrong order. You might be able to spot what it is. Can you see what I did wrong here? It seems like the way that I've listed out those differentials are incorrect based on the way that I've listed the bounds. Now, I'm going to go ahead and maybe just rewrite my bounds here really quickly. Notice that my x bounds should be first because that's the most integral, then my y bounds, and then my z bounds on the outside. Again, though, since this is a box, it's actually totally possible that I could have written things in that reverse order, and I would have just needed to maybe swap around the differentials at the back. And much like we worked over rectangular regions with double integrals, we could interchange things pretty simply. Okay. If we take a look down here at example 1, we can see how this might actually begin to play itself out. Suppose that B here is a rectangular box. The first question we would want to ask is, what is the geometrical meaning of this triple integral? Well, the cool thing there is I can start to identify again that the function there that I'm integrating is really just a 1. And so in the same way, when I did a double integral with a 1 as the function, I calculated an area. And so when I do this triple integral with a 1 in there, this represents the volume of the box B. Okay. So when I integrate a triple, or I do a triple integral with a 1 in there, that means I'm automatically going to be grabbing the volume of what I'm integrating over. Okay. So now we obviously won't always be working over something with a 1 in there. We might work like something here in part B. Evaluate this triple integral exactly where it's the case that B is this rectangular box. Okay, now again, this shouldn't actually be too terribly difficult because I can take this triple integral, x, y, z, and I should be able to re-express it. Let's see, maybe I do dx, then dy, then dz. I can put all of my bounds, all of my bounds on my integrals. And then I could just start integrating one at a time, just like I would have before. So I'll have this double integral sitting on the outside still, but I can do that innermost integral with respect to x. Of course, that's going to give me something like x squared yz all over 2, and I'll evaluate that from -2 to 1, and then I'll still have my dy dz after. I could then go ahead and attempt to integrate or simplify that interior, and I'll arrive at a nice double integral now. Notice I'm going to have a yz over 2, and then I'll have minus a 4yz over 2. Now, I could simplify this down a little bit further. I could write this as, let's see, it looks like I have -3 halves yz. Now, from here, I would ask you to see, can you take this the rest of the way, right? This will be something that I'll try to do very frequently within these videos. I'm going to ask you to just pause the video, see if you can work out the details on your own, and then hit play again to see me actually work through the rest of it, just so you can test to see if you're working through and understanding everything okay. Right. At this point, hopefully you've been able to see that the evaluation of a triple integral isn't necessarily any different than the evaluation of a double integral. I start at the innermost one, and I start working outwards. And once I arrive at a double integral, that's something that we've already seen. So pause the video here, and then see if you can actually work through and get to the same result that I'm going to get to. Okay, so here's what I would do if I was continuing on. I would end up with something like a -3/4 y squared times z. I would evaluate that from 0 to 2. That would get me an integral from -1 to 0. And when I plug in 2, I'm going to get 4, so it's going to be -3z dz. So that's going to be -3 halves z squared, evaluated from -1 to 0. So that's going to be 0 minus -3 halves. And so I got a total of 3 halves. Okay. So hopefully you got 3 halves as well. The thing that's kind of the most strange here is that what does this 3 halves represent? It doesn't represent the volume of the box because I didn't integrate with a function of just 1. So this represents some other value that at the present moment we don't have a geometrical notation for, but we will see in some of the sections later to come that we will come up with some meaning for what exactly something like this might actually be able to stand for. Okay, we'll pick up on the following definition and some of the different types of regions we can integrate over in the next video.